Believe it or not, some numbers are happy, and others? Well, they're trapped in a miserable, endless loop. But what's the difference? Today, we're going to be detectives. We're going to go on a mathematical investigation to uncover the secret that divides the happy numbers from the unhappy ones. So, what does it even mean for a number to be happy? I mean, obviously, it's not about feelings. It's about a very specific mathematical journey. And our job today is to follow that journey piece by piece and see exactly where it leads. Okay, first things first. Every good investigation needs a set of rules, right? So let's break down the process that determines, a number's emotional state, mathematically speaking. Here are the official rules of the game. You take any positive number, you square each of its digits individually. Then you add those squares together to get a whole new number. And you just keep doing that over and over again. If you eventually land on the number 1, congratulations, you just found yourself a happy number. To really see how this works, let's bring in our first subject for investigation, the number 19. So is it happy? Unhappy? Let's follow the evidence and find out. The journey of 19 is actually a really cool chain reaction. So first, 1 squared plus 9 squared gets us to 82. Then 82 becomes 68. Then 68 becomes 100. And then, finally, it lands on that one magic number. And there it is, the number 1. You could call this the definitive proof of happiness. See, once a number reaches 1, the process just stops, because 1 squared is always just 1, forever. It's a happy ending. The evidence is crystal clear. The process led directly to 1. We can say with absolute confidence, case closed. 19 is officially a happy number. But not all numbers find this happy ending. Some get lost along the way, trapped in a dark, complicated loop. And this brings us to the case of the never-ending number. Let's consider our next subject, the number 2. It seems simple enough, right? But its journey is very, very different from 19's. What do you think happens when we apply the rules here? Just watch the path of number 2. It jumps from 4 to 16 to 37. It keeps changing and morphing. But then, something weird happens. After a few more steps, it hits 20, and from there, it goes right back to 4. And just like that, it's caught. This number will now repeat this exact same sequence for all of eternity. It's completely trapped in a loop. And that, my friends, is the fate of an unhappy number. It gets caught in a cycle that never, ever reaches 1. It's just destined to repeat the same steps forever and ever. So this brings us to the real heart of our mystery. If we're writing a computer program to figure this out, how do we teach it to spot one of these infinite loops? I mean, we can't just let the program run forever, hoping it stops. We need a much smarter strategy. Okay, our first detective technique is all about memory. The best way to think about it is like leading breadcrumbs behind you as you walk through a forest. If you suddenly come across one of your own breadcrumbs, you've been there before. You're just walking in circles. So in programming, we call this the hash set method. We just create a list of all the breadcrumbs, which is every number we generate. At each new step, before we do anything else, we just check our list. Is the new number already on it? If it is, boom, we've found our loop. The number is unhappy. Simple as that. Now that first method works just fine, but let's talk about a different approach. This one is less about brute force memory and more about a really clever trick. It's often called the tortoise and the hare algorithm, and it is a beautiful, beautiful piece of logic. I want you to imagine 2 runners on a track. One, our tortoise, moves forward just 1 step at a time. The other, the hare, is way faster. It moves 2 steps at a time. We're going to have them both run along the sequence of numbers that we're generating. Now think about it for a second. If the path is just a straight line, the hare is just going to run off into the distance and they'll never meet. But if there's a loop, the fast runner is guaranteed to eventually come all the way around and lap the slow one. The moment they land on the exact same number at the exact same time, we've found our cycle. It's a mathematical certainty. Pretty neat, right? Okay, so now we have our 2 detective techniques, the breadcrumbs method and the 2-runner trick. Let's see how they really stack up against each other. In the 2-runner method, this single line of code is basically the heart of the whole detection. All it's saying is we're going to keep moving our slow and fast pointers forward until they are equal. If they meet, we stop and check. Did they meet at the number 1? If not, guess what? It's an unhappy loop. It's so simple and elegant. So here's the fundamental trade-off, right? The hash set method is super intuitive and easy to understand, but man, is it hungry for memory. The two-pointer method, on the other hand, is a bit more clever, a little harder to wrap your head around at first, but its biggest advantage is that it uses almost no extra memory at all. It's incredibly efficient. So we've solved the puzzle. But you might be wondering, okay, why does any of this matter? Is this just a fun brain teaser? Well, not exactly. There's actually a much bigger, much more important idea at play here. Because this entire time, we haven't just been talking about numbers. We've actually been using them to explore one of the most fundamental problems in all of computer science, cycle detection. So what's the key takeaway from all this? It's that happy numbers are way more than just a puzzle. They're a gateway to understanding a crucial concept: how to find hidden loops. You've now seen two powerful ways to do it: the simple memory paste method and the really clever two-pointer trick. And this isn't just theory. This exact same logic is used in the real world to protect databases from errors and keep huge computer networks from crashing. And that's our explainer. We've taken a seemingly simple puzzle and revealed the powerful logic hidden deep inside. So I'll just leave you with this one question. Now that you know how to spot them, what other problems in technology or even in your own life are secretly just